Good morning. This is Professor Packirisamy from Concordia University, Montreal, Canada. I thank you so much for inviting me to this fantastic conference, and especially Professor Chandrasekharan for inviting me to this wonderful conference, which has been happening for the past day now. So it's really my pleasure to be part of this conference now. So let me share the presentations. So today's my talk is going to be Microsystems for Internet of Things and Industry 4.0. This is because you've been listening to so many talks of on the upper level of Industry 4.0, Internet of Things. Why I'm coming from the lower level of sensors, which is the hardware flow, where we need to provide the data. That's where I am there. So start with acknowledgement to my students. And then to my funding agencies. So you all know there's evolution of industrial revolutions from 1.0 to 5.0 with artificial intelligence. We know this. So, but one critical element for this industry 4.0, from my point of view, is the data analytics, and especially the digital medicines, where I am more working towards hospital to home for industry 4.0. So which involves various devices, whether it's mobile or wearable devices, many of those, that's part of the system. So as you see here, for industry 4.0, the building blocks, there are various sensors, including 3D printing, which I work on, direct sound printing nowadays, and various devices, wearable devices, many of them as part of this industry 4.0. And if you look at the digitalization of medicines, where you're talking about, let's say, any health issues, and we need a lot of data, we need sensors, and then we need to connect the sensors to the Internet of Things. This is the way the whole power is coming. So we need mobile technologies which have integrated sensors, integrated or wearable devices, or ubiquitous arrangements. There is various applications of the same. So if we look at these capabilities of 4.0 in the medical field, you can see there's so many applications comes out of it, but all of them need one common thing, which we need the data of the patients. Okay, that's the bottom line. So that means the sensors. So sensors, you're looking at various sensors, passive sensors, like pressure sensors, various sensors, nano sensors, micro sensors, and wearable devices. There is so many sensors that comes in. And one of the work that we did is on bringing hospital to home is sensing devices which can automatically send signals to the cloud and then to IoT. This is what we are working on it. So from this basic introductions, two things come out very clearly. One is more and more sensors, which need to be reliable, small, portable, disposable, to be networked. This is very important. Then the integration aspects, like we should be able to integrate mechanical, electrical, optical, microfluidic, chemical, and many more functionalities into the same chip. So the integrations, the size, multiplicity, these are the keys for the sensors. So hereafter, I will focus more into the work that I do in Concordia University in Canada. So mostly the work involved in my lab. Okay, so I will focus on different types of work that we do and how they can be relevant to IoT and Industry 4.0. So this is my lab and the office, all in the same buildings. So is this a microsystems? What's a microsystems or any enabling technologies is basically the push is the development, technology development. The pull is application driven. Okay, so the more the applications, the field will grow more. So MEMS is something driven more by applications, and the Industry 4.0 is an ideal for that, to make MEMS grow more and more. So I work in the area of sensing and diagnosis, from molecular to cellular level, working with actuators, micro total analysis system, lab on a chip, and also micro nano integration engineering. So some of this biosensing element that I've been dealing with, it varies from molecular level, like antigen antibody, to cellular level. We have been working. So we have been doing a lot of this bio recognitions and biodeductions in my lab. And we have been using electrical, piezo, optical, mechanical, various ways of detecting it. Sometimes you see that labeled approaches, like where You you label those particles and just look at the fluorescence aspect of it, like ELISA, or you can have a label-free sensing methods where we are using SPR, okay, surface plasmonic resonance, or resonators, cantilevers, or any other optical way of doing it, like evanescence, and various ways that we have been working on. So what drives me? This is from Philip Sharp, who got a Nobel Prize. And he recommends that the third revolution life science can happen only when we can handle these challenges, like deal with the brain, nervous system, cardiovascular, cancer diagnosis, discoveries to the market, education. But this is only possible if we can work in a convergence mode where engineers, biologists, and physicists, all the people involved, work as in a convergence mode. This is the key here. So in this way, I've been working with a lot of doctors and life science people, and also a lot of engineers. So my job is to connect and create useful devices for useful applications. And this is what I've been working on. So is it easy to do? To find it very fascinating, because there is a scaling synergy that exists between biosystems and microengineering. For example, biosystems, you get molecules to cells, but dimensions go from nanometer to millimeters, for example. A micron cells, but you can go tissue level afterwards. But in microsystems also, we have methods to fabricate from nanometer to, for example, millimeter. Not only fabricate, to even characterize, test, we have techniques. So we have a common scaling synergy between bioengineering, biosystems, and microengineering. So, how I'm going to implement this? I'm implementing through the design of lab on a chip, where lab on a chip can cover anywhere from millimeter to hundreds of nanometers, and also micro nano integrations, which can go from micro nano integrations, which can take it from further nanometer, micron to nanometers level. So combining this micro nano integration lab on a chip, I could cover the entire range of applications of my systems. So one example I can tell you is micro nano integration, is where we integrate nanoparticles and nanoislands on top of microfluidic chip. Okay, so these nanoparticles could be immobilized with antibodies, which can be used to recognize antigens, and then further can be isolated for further detection. This is what we are doing it. And we did the same thing with carbon nanotubes on that, with the nanoparticles on top of the carbon nanotube, which is giving a very good sensing too. So I look into some of this way of implementing micro nano integrations. What is the nanopolymer composites? So a classical example I'll do with growth hormones reductions in milk. It's basically RBST, recombinant bovine somatotropin. It was done with a collaborator. They had met a company who was interested to make this product to identify, to detect basically growth hormones in milk. So we developed a protocol with the lab on a chip with the growth hormones reductions, and we could get up to 3.7 nanogram per ml, okay, which is much, much smaller than 100 nanogram per ml allowed in some countries, but most of the countries do not allow growth hormones, but few countries like US and Mexico do allow to a limit of 100 nanogram per ml. And we can go much smaller than that, which is 3.7 is the limit that we could see. What's the advantage of lab on a chip? If you look at the conventional type of technique like LCMS, HPLC, these techniques take a lot of time, days, weeks, and very expensive. But if you come up with the handheld devices like point of need applications, where you can give it to a farmer and you can measure it, and even collects the milk, that's the idea. We can do it in very short duration. So let's say half an hour time, that's going to be a great help. So that was the idea to do this. And we have done many of those deductions. Many of the devices have been tested. Many technologies have been developed on this. I'm not going to go through the detail of all of them, but you can go up to various sensitivity that you can get even up to 5 nanogram per ml. But one thing we did is we did a different technique, whether evanescence techniques to LSPR, which is localized surface plasmonic resonance techniques. And we found that LSPR is much more sensitive. Okay, so we are doing more on LSPR nowadays on those detections now. So this is a monolithically integrated lab on a chip. Very interesting concept here. It's a silicon chip. You can see here there's a single waveguide through which light comes in. The lights get splitted, and there's a microfluidic channel which passes the milk. Let's say pass a drop of milk. The light interacts with this milk. The information is collected by the light and goes to the spectrometer, and then you get the diffracted wavelength of the light. Okay, and this is on the whole spectrometer sampling and all the waveguides all done in a single chip of basically 5 centimeter by 1 centimeter. This is something very interesting to miniaturize big equipment. So we can also further miniaturize this into a plastics. Now this is a plastic chip of the same. And finally, what is here is we could miniaturize bigger equipments with the whole lab. For example, the entire lab that you have into a tiny chip. This is what we are doing. Now you can see the power that can be applied to IoT or Industry 4.0. The information that you can process with these chips can be sent into the network. That'll be amazing for us. So this is what it is, lab on a chip for RPST biodetection. That's a chip which does all this. So we have done a few patents on this. Also, there are many technologies that on a lab on a chip can be used to detect antigen antibody interactions, which can be used for various detection of biospecies. One we tried to apply was malaria detections for this. And again, from the fluorescence detections, one can identify that. There's another detection is a heat shock protein IT and ATP interactions, which is done through bioresistive sensing. So whenever the cells get stressed, then they release a heat shock protein. Then identification of that, they undergo a conformal transformation, the heat shock protein. So here to identify the conformal transformations, we made this chip for them, which is also good for various bio applications. Then what is a lab on a chip? So let's say we all live in a home and we are very comfortable in our home. We have food, we have kitchen, we have oxygen, heating, everything we have at home. But if I want to provide the same thing to the cells in a tiny chip. So we grow the cells and manipulate, culture everything inside this microfluidic chip, where you can supply the nutrients, carbon dioxide, oxygen, air conditioning, heating, everything can be supplied so that to make those cells cozy and livable conditions for them. This is my idea, so that you can manipulate, you can study them as if they are in the real living system. So this is one of the typical chips we're talking about, microfluidic chips, various inputs, outputs for the fluids to go through, and cells will be trapped inside. We can manipulate the cells, you can trap the cells, manipulate, understand the behavior. You can also subject to various conditions, environmental conditions, and then study the behavior in relation to the environments. This is something interesting aspect of this. One of the good example could be energy harvesting, which is the photosynthetic electrochemical cells. From here, we all know that in a plant, when the light falls, the chlorophyll converts photons to photosynthesis. In the process, every photon that gets absorbed, you get actually electrons released as part of the redox reaction that happens in the photosynthesis. The idea is if we can trap those electrons out of these, then we can produce electricity. So that's what we are trying to do. And we did it in a microfluidic chip. So this is a chip. We can see top chamber is filled with algae. Bottom chamber is a reducing agent. And then the proton exchange membrane in between. And then this is microfluidic chip. And then you can see some of these, the power characteristics that we obtain for these microphotosynthetic cells. And very interesting thing is they could be scalable. They're very scalable. And we can also scale them to various levels to charge phones and various other devices. Okay, this is a very good green way of energy harvesting from photosynthesis of algae. So another application of lab on a chip is a pollen tube study. You can see this is a pollen tube, germinates from the pollens. This is the pollens. Thanks to Dr. Professor, actually, Anya Gateman for this picture. It's a beautiful picture there. So here, what happens in a pollen here, when the pollen grain sits on the flower, stigma here, let's say here, as you see here, and it germinates a pollen tube. This pollen tube keeps drilling inside the flower stigma, finally reaches the ovule here, and to release this sperm cells into the ovule. So we're trying to understand the morphogenesis of this pollen tube, how they grow, what's the pressure inside, why should they take turn, what makes them to bioselectivity of selecting organisms, and various fundamental questions. We wanted to answer them, and we could do that. We could do that by making the lab on a chip. So we fabricate a lab on a chip, as the way I told you before. And you can see here, this is a, you can see this is a pollen grinds, and these are the pollen tubes grow inside the microfluidic channel. The pollen grinds, pollen tubes are typically 17 microns or 15 microns in size. They're very, very tiny, okay? And so interesting thing is we can trap each cell in a particular location and make them grow in the direction we want and control the behavior and characterize them the way we want. That's something, it's a beauty of this chip. This is where the chips are. Now, next step, what we did is very interesting thing. We make the pollen grinds. So pollen tube grow in a particular direction and make it to hit microcantilever. So when the pollen hits a microcantilever, it bends the microcantilever. So leading to, we can even find the pressure, mechanical force exerted by the pollen tube. This was a very good method of directly finding it. Mechanical force exerted by these pollen tubes. So there are other various applications that are being done with the lab on chips, and like enzymes and detection of enzymatic detections, where we use the cantilevers. And so anti-enzyme reactions happens on a cantilever, and because of the biomechanical stresses produced due to the interactions, the cantilever deflect. From the deflections, one can find a deflection pattern, one can find the behavior that happens, and you can detect what kind of interaction that happens. You can use to detect various analytes and various sensing and diagnosis is possible. So we use the technique for different types of cancers. We're very successful with that technique, identifying with a blind test. And so if you look at all these sensors that has been used to biophysical study, there are various types of sensor, and one of them is microcantilever sensor. Okay, the microcantilever sensor is quite a bit. And the latest one is actually here, suspended microfluidic resonator, which is the new one, which is, so if you look at the x-axis, it's talking about time, y-axis is the limit of detection. So understanding what this idea here is, you want to go less time as possible and lowest limit as possible. So we are trying to aim towards this origin. So we are trying to move closer to this. We are trying to move closer to this. How can you move closer to this? And this is what we are doing. So you can see that for microcantilever going suspended microfluidic resonator going. So we like to go much more than that in our study. So we did this microcantilever based sensing, which has again lots of applications for Industry 4.0. So this is like microcantilevers, tiny cantilevers of microns of sizes as usual. And you make the bio interactions happens on this surface, and then as it happens, you study the vibration pattern or study the static deflections, any mechanical behavior one can study and identify. So we started with a simple atomic force microscopy for this kind of detection. Then finally, then the data is they even detect to E. coli, the mass of one E. coli bacteria that could detect. Then they get a suspended microfluidics. That means you can put the microfluidics inside the cantilever, suspended cantilever. So we can also do microcantilever interaction studies. It opens up a huge area, because when you put the cantilever inside the microfluidic, then the fluid interactions around the cantilever is huge. It's difficult to use, and it's not easy. But if you put the microfluidics inside the microcantilever, then it's much more cleaner, neat way of doing it. Then we improved further sensitivity by using suspended and polymer-based microfluidics and also three-dimensional based microfluidics after that. Okay, this is one nice example of E. coli bacteria attached to the cell. We can measure the mass of a single E. coli. It was done a long time back by Craig. So we done many work in a similar way of the cantilever, as I told you, just cantilevers, and we applied it for various applications for antigen antibody interactions. And we did it for troponin C, melatonin B structures. We did it. And we got various enzymatic reaction results. From this signature analysis of this, one can find out what kind of reaction goes on, what's the strength, all that one can easily detect from this. Then we developed the polymeric suspended microfluidics. You can see there is a, let me take that highlighter, laser pointer. So you can see this microfluidic comes through this, and then it goes, and this is suspended cantilever here. Microfluidics is inside this. You can see the cross section of the channels here through which the fluid goes in. Okay. So that's a fabricated suspended. So here what you do is we are doing the antigen antibody we are doing that antigen antibody interactions inside this cantilever. You can see that cantilever will deflect from there. You can detect the concentration of the interactions and concentration of the analyte, basically. So we use this cantilever for detection of growth hormones again. This is what we did. Okay, so not to improve the sensitivity, what we've done, interesting thing here is we integrated nanoparticle inside this microfluidic channel. So all the microfluidic surfaces were integrated with nanocomposites. You can see all this gold nanoparticles on these microfluidic channels. And these gold nanoparticles are used to immobilize antigen, basically antibody of growth hormones, to detect the growth hormones. And from there, you can detect the growth hormones from the deflection of this. So we could get up to 2 nanogram per ml detection was possible, which was never done before. This is one of the least so far achieved in detection of growth hormones in milk with this type of device. Then we developed a 3-dimensional microfluidics because we wanted to improve the deflection to make it more sensitive. We basically turned that microfluidics into 3-dimensional pattern. So we got the 3-dimensional microfluidics, and which gave much more flexibility and much more sensitivity for us to do. And you can see that's a nozzle here at the 3-dimensional way. When the fluid goes, it produces a force which leads to deflection of these cantilevers. And very interesting thing is when we did that experiment with the different fluids, the Newtonian and non-Newtonian fluids, that's a beauty here. So Newtonian, non-Newtonian fluids, in terms of kinematic viscosity, you got a beautiful only one graph. Okay, so the system is more insensitive to that Newtonian or non-Newtonian fluid. That's something very interesting that we found out, and it matched so well with modeling and predictions. And later, we can also pass through different cells or different bubbles and find the elasticity of the cells. We can use it for cell counting, cellular properties, the deformation of the cells, all could be obtained from the way the cantilever are deflecting. That's something very, very interesting for us to know. And we did different effective nozzles to come up with a different sensitivity on this. And we also used it to count the particles. Whenever the number of particles goes through, so these particles will flow through, and whenever the particle flow through, will create abstraction, leads to force, so we can count from the deflection of the cantilever's number of particles, sort of a flow cytometry, I would call it. So you can see that the particle goes through the microcantilever, and then as they go through this apertures, they come up and then go upwards. So that's a 3-dimensional nature of this microfluidic channels here. So you can also find the flow velocity and also number, kinematic viscosity, and cellular properties. It has applications in various domains. Then some devices we did for basically telerobotic surgeries. And this is a new area for minimally invasive surgery in terms of endoscopic grasper or tactile sensors or various other minimally invasive surgeries. So we developed various tools, basically miniaturizing these endoscopic graspers and laparoscopic for laparoscopic applications. We have done few work. So this basically want to give the feel of touch to the surgeon, because now the surgeon doesn't have the feel of touch. He only has a visual feedback, but no tactile feedback. So what you're trying to do here is provide the tactile feedback to the surgeon. It's almost putting the finger inside the body, feel it. So we are doing that, and we did various applications. We have come up with various devices, electrical-based devices, and also fully optical-based devices. Because when you in a medical emergency room, generally they want electrically passive devices. Also, the EMI compatible, electromagnetic interference compatible. So they don't want usually electrical devices inside. So in order to comply with that, we moved away from this piezoelectric based tactile sensors to optical sensors later. Okay, so if you look at these piezoelectric tactile sensors, basically you're grasping that, you're grasping the object. You're grasping the object here. When you try to skews, basically you can measure the softness of it. Okay, and you can also use to feel the tumor inside, and one can find the tumor size, locations, depth, all that from this from these sensors, which is very, very powerful device for that. And we also did fully optical based tactile sensors, where there's no electrical involved. We have done lots of work on that. Like, this is all done with optical fibers here. You can see, and there's a silicon membrane. So deflection of the silicon membrane is converted to softness, and the force sensing and the location sensing, all that is part of it in this case. You can see this is a close-up of the devices that what we made and what we tested it. Okay, so we have been working on various applications of grasping and the softness sensing and force sensing with this. Okay, so one of the grasper that we are looking at, the new design is something like this, and we can see there's a grasper, there's optical fiber there. The bending of optical fiber gives basically the deflections, locations, and many such parameters, including the softness of it. Okay, so we can see that this is a device that has been fabricated, prototyped, and now this can be easily wireless transferred, and then all the devices that we're talking about here could be wirelessly transfer the signals to places that we need. That's something beauty of it. And here you can see there's endoscopic grasping some sort of a tissue or a meat to find out stiffness. A student did the work. Good work done by the students. Okay, and this also for lateral force displacement is fully optical device. Has been developed with the cardio doctors, and you can also measure the lateral displacement. So basically, if something goes in artery and you want to measure the stiffness of arteries and various applications where the lateral force becomes tricky to measure. This is meant for that lateral force measurement system. Then we did more work on nanoparticles, interaction of nanoparticles with the cancer and non-cancer cells, because the cancer cells, this is a big problem. It's not something you all know, but nanoparticle has a huge applications in terms of drug delivery into the system, and even much more than that. So we have done a lot of this nanoparticle interactions with the cancer cells. So we synthesize our own nanoparticles, and also we work with Indian Swarnabhashma, which is Ayurvedic gold nanoparticle. We call it gold ash in India. So because we know that Indian system, Ayurvedic and Siddha system, in India, Ayurvedic and Siddha system, they have been using Swarnabhashma for many, many years in curing cancers of different types. I talked to various doctors, and that's the information. And they're sure that it works. The only thing, how it works, and there's so much questions on the safety and toxicity effect of these and all that. So I wanted to inquire fundamentally into this work and the effect of these nanoparticles, Swarnabhashma, into the cells and cellular behavior. So we did work with the HeLa cells, and you can see the nanoparticles inside the HeLa cells. And the interesting thing is these nanoparticles enter well into the cells and even into the nucleus, depending upon the size or so. But this gold ash or sonobashma was also able to enter into the cells. One thing we found out is these nanoparticles are not toxic. This is what we found out. And the cells knows how to handle them. They use it or they don't use it. They just dispose it off. This is what you can see, all the black dots, the nanoparticles. They are some of them inside, some of them outside the cells. It has been published in Nature Scientific Report and also covered by Nature India a long time back. This opens up a big area of looking into Siddha Ayurvedic studies in a more systematic way. And I think which also, in my opinion, has a huge applications for Industry 4.0 and IoT, because that's something India has a power in it. I think we should look more into that too. So you can see that sonobashma, you can see the sonobashmas that indicated by arrows in HeLa cells. They enter very well into the cells, even they enter into the nucleus. When the nucleus divide, and they also got divided into two cells, something very interesting. And we also saw them in various other cells, not only cervical cells, liver cancer cells, lung cancer cells. The work has been done various cancer cells, and we understand how these nanoparticles behave and interfere with the mechanism of cells. Okay, so it has been done on various cells. We've done it with the nanosphere, sonobashma, nanostar, and all this, the morphology of the cells as a different behavior of these cells. You can see this, the plasmonic response of these particles inside the cell. This is we call the intracellular plasmonic. This is something we proposed from our lab. Intracellular plasmonics, a new area. By looking at the plasmonics of cells absorbed into the cells, one can identify the condition of the cells. This is what we are looking into more and more in future. Okay, so one of the good example I want to say now is detection of isolation of exosomes. Okay, what are the exosomes? Exosomes, as you see here, the extracellular space, every cell release some sort of a nanoparticle, almost a virus size, 100 nanometer size, let's say. These bioparticles called exosomes or extracellular vesicles, the exosomes, let's stick to the term exosomes, they carry a lot of genetic informations of the cells. Okay, if they come from cancer cells, they carry a lot of cancer genetic informations. They come from good cells, then they carry good cell informations. And these nanoparticles, these exosomes always released by cells, they get into the bloodstream, they go into the bloodstream, and wherever they land up, they can convert that cell into cancer cells. This is the metastasis happens. Okay, so recently it has been found out that exosomes play a big role in metastasis of cancer. So if we can detect the exosomes well in advance, I think the chances for cure is much, much better. So this is what we are doing, ultra early diagnosis of cancer, which can do with any body fluids, whether blood, urine, saliva, breast milk, any of those body fluids we can detect with. So there are various ways right now, but we are trying to find out using lab-on-a-chip concept here. That's what we are interested in, microfluidic-based chip. Okay, so we are using LSPR-based lab-on-a-chip concept. There are various methods, but we are interested in LSPR, localized surface plasmonic resonance, and LOC, lab-on-a-chip concept here. Okay, so here what we do is we just follow the antigen-antibody binding principle. So we have a VN96 as our antibody for that, and which has been tagged with the peptide here, VN96 peptide. This has been tagged with the streptavidin and the biotin. So we have this strong binding between streptavidin by biotin bonding is being used for detecting this detect these exosomes, because exosomes have a strong binding with VN96. So as you can see here, as a gold nanoparticle we have, to your various process, every process layer gets immobilized. Finally, you get a plasmonic shift. The plasmonic shift is here. So measure the plasmonic shift. that indicates a concentration of the exosomes, which indicates the stage of the cancer for us. So by looking at the concentration of the exosomes, one can identify the stage of the cancer, can be used for very early diagnosis. So we are interested, our work is here in this way. Okay, so we can see here some of the concentration of the exosomes with LSPR chip that we got. So in a no cancerous patients, we are somewhere here, the concentration of exosomes here. With a fully cancer patient, stage 4, the cancer here. So if you can monitor the concentration of the exosomes, then we can completely follow the development of cancer throughout. Okay. Now we are also working much more deeper in this. It's not only concentration, the quality of exosomes and what kind of cancer it is. It's a mind-boggling field right now with the potentials on this. And a lot of my students work in this area right now in this. Okay. So, so this is what the microfluidic chip is. We can see the microfluidic chip and the gold nano integrated microfluidic chip, and the flow goes through it, and we can use it for detecting it. So basically what we learned now is my lab works on developing small devices for point of care, point of need application, which are the ideal devices for IoT and Industry 4.0 applications. Not only for health, they also could be applied for non-health applications too. So in simple terms, what I try to do is I'm trying to shrink the elephant, the power of the elephant, into a honeybee. And not only simple honeybee nowadays, nano integrated, decorated honeybees. So this is what my research is. I hope you enjoyed. And I'm really sorry that I couldn't be there physically with you today, even though I planned to be there. And due to family reasons, I couldn't be there. I hope some other time I'll be able to meet you all. And this is finally, when I make a chip, I want to shrink the entire hospital into a chip so that each one can carry the hospital in the pockets. This is called hospital to home concept that we work. You can see the potential of such technologies for Industry 4.0 and IoT. And thank you so much for listening.